New York by the Hudson River, amidst the complex infrastructure spanning over the rail lines, a single curved blossom has risen. 15 Hudson Yards, 278 meters tall with a total of 88 floors. Beyond its graceful curves and glass curtain wall, this building is not merely the result of design. To support the beauty of its curves, hundreds of tons of load were calculated, thousands of columns and slabs were meticulously planned, and countless technical challenges were faced on site. This video follows the construction journey of 15 Hudson Yards, tracing the challenges encountered during the building process and the structural solutions that overcame them. What we aim to tell is not a story of beauty, but a record of engineering that made that beauty possible. To support its massive loads, 15 Hudson Yards employs a structural system composed of a central reinforced concrete core combined with a network of perimeter columns. The core serves as both the structural center and the heart of building system for resisting wind and seismic loads. The perimeter columns are arranged along the building's exterior, distributing gravity loads and playing a secondary role in resisting lateral forces. However, columns alone were not enough. To ensure the building's overall lateral stiffness, key mechanical floors were equipped with outrigger walls and belt walls, horizontally linking the central core to the perimeter columns. According to design standards, over 70% of the total lateral load is resisted by the central core alone. From here on, we will take a closer, in-depth look at each component that makes up the structural system of 15 Hudson Yards. 15 Hudson Yards is a super tall structure rising 88 stories above ground, bearing total loads amounting to several thousand tons. That weight does not simply travel straight down in a linear path. The loads originating from the slabs travel down through the perimeter columns and central core, then pass into the lower transfer structures, and are ultimately distributed through the mat slab into the caissons and to the bedrock below. However, this structure is not perfectly symmetrical. That's because part of the lower structure had to be left open to integrate the shed, an open cultural space. In such an asymmetrical structure, loads tend to shift to one side, creating eccentric loading and overturning moments. To counter this, a massive mat slab was installed at the base of the building. This wide and thick reinforced concrete mat acts as a structural buffer, spreading the loads over a large area and evenly transferring them to foundation points such as pile caps and caissons. And what ties these mat slabs together horizontally is the tie beam. The tie beam enables the entire foundation to act as a unified system, redistributing stresses and ensuring structural integrity when subjected to seismic forces, wind loads, or eccentric loading. But it doesn't end here. The lower 8 floors are occupied by the shed's mechanical rooms and back-of-house areas, and due to its movable roof structure, a column-free open space had to be created in lower levels. This challenge was addressed through the use of K-shaped incline transfer columns. K-shaped transfer columns combine vertical and incline members in a K configuration, redirecting upper-level loads toward the perimeter or central core. And tying all these structural elements together is the diaphragm slab. The diaphragm slab provides horizontal stiffness and functions like a beam in the horizontal plane, distributing lateral loads to the perimeter and the core. When wind hits one side of the building, the pressure exerted on the windward perimeter columns and the curtain wall is transferred into the slab at that level, which then simultaneously distributes the force to the central core walls and the columns on the opposite side. At this point, the slab develops in-plane shear as well as tensile and compressive forces. On one hand, channeling the majority of the lateral load toward the core, and on the other, tying all the columns together so the entire building moves as a unified system. It acts like a structural system that binds the entire building together into a rigid unified plate. Thanks to these connection techniques, the area beneath the shed could remain entirely column-free while still supporting the stable upper structure above. Another challenge was that 15 Hudson Yards was designed to be built right next to the Amtrak tunnel. The closest distance between the Amtrak tunnel and the foundation of 15 Hudson Yards is approximately 30 centimeters, which is a remarkably tight proximity. Due to this extremely close construction condition, high vibration methods were completely avoided during the casing installation for 15 Hudson Yards. Instead, quiet and stable techniques such as lotary drilling, core drilling, and channel drilling followed by rock splitting were employed. To avoid direct interference with the Amtrak tunnel, the casings were positioned with precision down to the nearest few inches. During rock excavation, strict vibration mitigation measures were implemented for drilling equipments to ensure that vibration would not transfer to the tunnel structure. Thanks to this precise construction and continuous monitoring, the Amtrak tunnel remained structurally unaffected and fully operational throughout the construction period, while the foundation work for 15 Hudson Yards was also successfully completed within the planned parameters. Tall buildings must also be equipped with structural solutions to withstand horizontal forces, such as wind and earthquakes. The lateral force resisting system of 15 Hudson Yards is not a single structure, but a combination of the central core, perimeter columns, and the complex mechanism that links them together. At the heart of the system is the reinforced concrete central core. Often referred to as the heart of the building, this core acts as a primary resistor against all lateral forces. However, the core alone was not sufficient. On intermediate levels such as the mechanical floors, an outrigger wall and belt wall system was designed to horizontally connect the core to the perimeter columns. This system, when the building is subjected to the lateral loads, transfers the rotational moment acting on the core to the perimeter columns, thereby reducing the building's overall lateral deformation. In other words, the outrigger distributes the forces, while the belt wall spreads those forces across the entire perimeter. It's a coordinated structural system where the core doesn't resist alone. The entire building envelope works together to withstand the forces. This structure is a key strategy, specially designed to address uplift, a characteristic challenge in super tall buildings caused by overturning moments. An overturning moment occurs when wind or seismic forces generate uplift on one side of the building's foundation. To address this, 15 Hudson Yards implemented the following structural solutions. First, the building's own self-weight helps anchor it to the foundation with high-strength reinforced concrete and then structural members providing resistance against overturning. Second, the massive mat slab integrates the foundation into a single unified platform, ensuring that even if one side experiences uplift, the entire base remains grounded, providing overall structural stability. Third, the tie-beam network acts as a mechanism for distributing overturning moments by linking different parts of the foundation together. Fourth, the caisson foundations, which is extending approximately from 18 to 24 meters deep down to the Manhattan bedrock, provide effective resistance against uplift forces, strong winds, shifting ground. Despite all these variables, 15 Hudson Yards secured its stability through its own weight and thoughtful design. So now, shall we take a deeper look into the foundation of 15 Hudson Yards? All the loads of 15 Hudson Yards must ultimately be transferred deep into the bedrock below. The challenge, however, was that this building was constructed directly above existing rail infrastructure. In this situation, where the foundation could not be freely placed, the design team opted for a composite foundation system consisting of drilling caissons, pile caps, and a mat slab. First, caissons are drilled from 18 to 24 meters deep into Manhattan's hard bedrock, known as the Manhattan Schist. The caissons have a diameter of approximately from 1.2 to 1.5 meters and were precisely installed to avoid interference with the Amtrak tunnels. On top of these caissons, pile caps are installed to integrate multiple piles into a single structural unit. Pile caps are thick reinforced concrete blocks that evenly distribute the loads coming down from the mat slab onto multiple caissons beneath them. It functions much like tying multiple bridge piers to a single footing, spreading the overall load across the wider area. Especially near the central core, where loads are most concentrated, multiple caissons are connected through a single pile cap, effectively countering overturning moments and eccentric loading. Above these pile caps, smaller columns are constructed, and on top of them rests the massive mat slab. The mat slab disperses loads across the broad area, enabling the entire foundation to function as a unified structural plate. The smaller columns, in turn, channel the concentrated loads from the slab down into the pile caps. And all of these foundation components are horizontally connected through a tie beam network, ensuring that even in the event of uplift or differential settlement, the entire system maintains unified structural resistance. What's crucial is that the building's loads are not transferred to the shared platform deck, but instead travel directly to the bedrock via the dedicated foundation system. In this way, 5th and Hudson Yards stands firm atop a dense urban infrastructure supported by a meticulously engineered foundation system that allows the flow of loads to proceed uninterrupted even in the most complex structural environment. One of the most fundamental conditions in constructing a building is this: how materials are brought in and where they are stored. But 15 Hudson Yards was constructed on a site where even such basic conditions were not allowed. The site of this building sat atop an extremely complex transportation infrastructure, with dozens of Amtrak and LIRR trains passing beneath it each day. As a result, material deliveries at ground level was strictly prohibited. There were no access routes for trucks and no available space on site to store construction materials. Even the timing of material deliveries were restricted after 10 p.m. when train operations came to a halt. To overcome these extreme constraints, the construction team implemented 3 parallel strategies. First, a massive steel platform was constructed over active rail tracks. This deck safely covered the rail lines and served as a working platform above, where materials could be unloaded and assembled. A tower crane was installed on this platform, enabling vertical lifting of materials and their distribution to the upper levels. Second, a just-in-time material delivery system was implemented. Instead of stockpiling materials on site, only the exact quantities needed were delivered during the nighttime hours and used immediately, minimizing storage needs and maximizing efficiency. Third, prefabrication was actively adopted. For example, components such as transfer trusses, curtain wall units, and piping modules were pre-manufactured in factories so that only assembly were required on site. Even the curved glass panels were manufactured flat in the factory and then cold warped on site to fit the building's curved surfaces. Unlike the conventional hot bending method, which involves shaping glass at high temperatures, this was a strategic choice aimed at reducing manufacturing costs and simplifying the construction process. Finally, because the limited space made a single crane insufficient, multiple tower cranes and external hoist system were operated simultaneously to manage material handling efficiently. This allowed materials to be lifted in multiple zones simultaneously, enabling parallel workflows on both the exterior and interior construction processes. In this way, the construction of 15 Hudson Yards demonstrated true technical mastery, not simply in building the structure, but in beginning with how materials would be brought in, shaping the design, determining the structural system, and orchestrating the construction process accordingly. From next week, we'll explore the overall structure of our main feature, the shed. And the following topics are gonna be discussed for the rest weeks. Thank you for watching.